solicit those issues perhaps even from the not usual suspects here in the audience at first. And then if people feel moved to make at most elevated pitch, informed, opinionated statements on that topic, perhaps you can move that way. So as issues, let me just make a start, put one down where I be not that close to feel. I have yet to understand on the theoretical or observational side how much all of what we've heard this morning actually does suppress star formation in disks, since I'm a firm believer that the majority of all stars at most epochs formed in disks. So we don't need to discuss it now. I'd be happy to either see theoretical or observational arguments for AGN suppressing. Can you turn off the projector thingy? Disk SF. Okay. Anybody else who would like to put an issue that we should return to from this morning? Okay, Rachel.
So, my own opinion, perception, whatever, is that there's at least 3 or 4 different processes that are regulating the growth of the black hole, regulating the growth of galaxies, solving the overcooling problem for the hot intercluster medium, and that these may well all be different manifestations of AGN feedback. And we've sort of heard from simulators, none of whom are putting in all of these processes, right? So the processes include Compton heating, winds driven by radiation pressure on free electrons, winds driven by radiation pressure on dust. These are going to arise from different scales. Then we have the whole issue of the radio jet feedback, which we have a whole session on in the afternoon. So I would almost argue that, if you're doing a simulation where you're just dumping thermal energy in, I would almost be more disturbed if that did fit all of the observations. So I think, some of the issues that Romain, for example, was bringing up, that, okay, maybe you can fit one set of observations, but not others. This is to be expected, right? And we can start to piece together, I think, from these different simulations, perhaps, which processes are most important for these different kinds of observations. But I'm curious.
Is that what you said that you would like? You think this?
No, I don't want it.
No.
I don't want. Well, I guess if anyone wants to defend this model, they can. But I guess what might be more interesting would be to think about which physical mechanisms are driving which observations. I think we have some insights into that. But
I'm happy to. Which processes map? But these are which AGN originating processes, only those, right?
Yeah, let's focus on that, because, we could go into all sorts of other things, but AGN are complicated enough.
Okay. Or,
and I guess in particular, if a thermal feedback only model overdoes AGN feedback, right, then that's definitely bad.
okay.
In the sense that you like there to be room for radio mode also.
Well, not necessarily, right? Because there's always a free parameter. And so if you're trying to do the whole job with just thermal feedback and you've cranked it up,
Yeah, you crank it down.
maybe it's
Hang on,
expected.
let's put 1 or 2 more issues on, and then we can jump into that phase. Are there any things that came up in the morning and you didn't have a chance to get back to you?
It's a more specific point, but whenever we have these questions and observations about relating properties, like Nadia was talking about, on some large scale with AGN, it's worried about AGN variability.
Yes.
The time scale in which AGN vary is usually smaller than the time scale over which the wind can affect these objects. So can you actually say anything about whether it's related to the AGN or not?
So there's both variability and the time scale for the AGN phenomenon.
Yeah, I mean particularly in the interpretation of observations.
Okay.
Yeah, duty cycle to that as well.
Is that the same?
It's implicit.
Okay. Okay. Anything else? Otherwise, we can get going on that one. Let's perhaps take it from that. And perhaps none of you want to comment on how much, what your observations, for example, say about the duration of the AGN episodes that are needed.
Right. Okay, so I want to make two comments. One is about the arguments for AGN suppressing disk star formation. I have a bit less to say about variability, but I will say what I have to say. So for AGN suppressing disk star formation, observationally, the methods that we would use to try to do that would be to look at the spatially resolved observations of disks, preferably at high redshifts, which is when AGN made the greatest impact on the formation of massive galaxies, and then look for any signatures that AGN-driven winds are suppressing star formation diagnostics. And such work has been done by various groups, especially using near-infrared IFUs, using Symphony and NIFS on Gemini. And there is some very interesting work by Cano Diaz in which they demonstrate that in regions where the velocity dispersion of the quasi-ionized gas is highest, the star formation diagnostics seem to be suppressed. We are seeing this at low redshifts in a statistical sense, again seeing that in objects which show the highest velocity dispersion of O3 emission lines, we see the lowest O2 to O3 ratios, thinking that O2 is probably at least in part related to star formation.
Can I just quickly ask there, I imagine that at a few kiloparsecs out, the enormous line width come from gas that is well above and below the disk. But you're saying there is actually, if I think of it looking in projection, in the regions, if I were to look face on, where I see the allegedly spherical bubble coming out, in projection there's less star formation in the disk. Right? You kind of describe your wind as approximately spherical.
Right. So I'm talking about two different things. So the Cano Diaz paper looks at one particular high redshift face on this galaxy, and they presumably would not be able to see the bubble if it were face on. So they only see stuff, in projection on the disk, and so we have no way of knowing the depth of the stuff in there, but they do see some relationship between suppressed star formation and the velocity dispersion of the presumably quasi-driven gas. The things that we are seeing in low redshift objects, we don't have any spatial information whatsoever. We're making a statistical statement saying that in objects where the evidence for quasi-driven winds is highest, we see the lowest amount of star formation in those host galaxies, but that needs to be checked and rechecked and rechecked again. This is very new, okay? This is all stuff within the last year, and it's not even clear to me that O2 is actually the right way of addressing this issue. I welcome suggestions for trying other measures.
Yeah, I see hands go up probably on that point in the back. Kevin, perhaps?
Yeah, so I think from a statistical sense at low redshift, I think you can make a fairly compelling argument that the simple equation of AGN turns on and star formation at disk, that doesn't happen. And so it's sort of related to the third point. So the characteristic timescale of the AGN is so much faster than the dynamical timescale of the star forming disks that an AGN quenching episode is effectively instantaneous quenching of the disk. And so you can ask the question, do you see any disk galaxies where star formation has been rapidly shut off? And the answer is, you don't really see that. And if you ask the converse, what are the galaxies like that have just shut off their star formation rapidly? They're either disturbed or they have some bulge. So if AGN shut down star formation in disks, it has to be accompanied by some sort of morphological transformation. And so the poster child of that in the local universe is, if you look at NGC 1068, powerful local AGN, really well studied. We see the outflow, we see the jet, we see everything, and as far as we can tell, it's basically just rearranging some stuff in the center. It's not going to turn 1068 into a dead disk or an S0 or something like that in the next 10 to 8 years.
Okay, good. Phil?
First, a comment on the variability. I just wanted to point to, there was a nice paper, I thought, by Ryan Hickox making a point.
Yes.
And basically the point there was just how dramatically this can influence our inferences. If you do, as many people have done, take an AGN selected sample and measure star formation rates in that sample, you get a well-known result that, except possibly in the quasars, there's no correlation between star formation and AGN activity. But if you select on star formation, you get actually a quite strong correlation that's sort of order linear AGN accretion rates, but with a huge scatter is the point. And the ignorance of that huge scatter can really bias studies depending on how they do the selection. And the information's in our AGN selected samples, we just have to be very careful how we model it and accounting for that. And people have made similar points about trying to measure the evolution of the M-sigma relation. It can be totally screwed up if you don't account for scatter in these correlations. So I just wanted to mention that and say we do need to take account of that. And then, yeah, the second point was just basically going to be what Kevin just said. I think we need to be careful about this argument about suppressing disk star formation. I don't think you expect in any of the models that if you turn on an AGN in the middle of a gas-rich thin disk, even the most optimistic models, it's going to find the path of least resistance. So I agree that there has to be something else happening. Yeah.
Okay, Arjen?
I think we need suppression of star formation in disks, right? Then disks have other ways to stop forming stars. If you reach a certain mass, the whole thing around the stable next door, and then you're in business.
I don't think that's...
It's just an idea. Do we need that?
The same
Well,
to,
that's kind of the topic of Thursday, so hopefully we will be able to answer that
We need
question.
something to stop gas from getting into the disk.
Yeah,
so-
that's the crucial one. We just
Okay,
need to stop
uh,
that.
Jay and then Rachel?
So 2 points. First of all, the AGN can greatly raise the cosmic ray pressure, which will diffuse through the disk. And potentially you can therefore decrease, well, you've added an additional pressure term physically. And that can change the star formation and certainly can change the degree to which the galaxy is accreting from its surroundings if you expand out. Secondly, in some disks, and we know this from the various studies, Mars, for example, are very open. They have a lot of material escaping out of the disk into the lower atmosphere from the whole disk. So it does seem you can change disks from a fairly closed to an open state where they're losing more mass. And these indeed have your almost spherical rings, but they're very small.
One more comment on the observational side is, in terms of the time scale for AGN, basically the winds propagate with 1,000 kilometers a second, and in order to get to 10 kiloparsecs, they need to translate 10 to the 7 years. And we have run various scenarios to try to figure out if we can get around this number, and we can't. This is it. If you see gas that's kinematically disturbed at 10 kiloparsecs, unless it originated right there, and it is just being lifted up by the shock that just got there, but then it takes 10 to the 7 years for the shock to have just gotten there. So no matter how you try to circumvent that, if we see disturbed gas at 10 kiloparsecs, 10 to the 7 is the scale, is the time scale.
But you're not unhappy about the coincidence that 10 to the 7 is not a bad time scale for AGN duration, or? Well,
I am not yet unhappy. Maybe with additional data, I will get, I will see more tension. We're definitely worrying about the time scale. We want to make sure that we are probing all kinds of, our observational program at this point is trying to probe different phases of this process and find the earlier stages and the later stages of this.
So the later
Rachel?
stages may be difficult then if the variability is 10 to 7 years. Because you wouldn't be looking for the brightest AGN, and you should be looking for the less bright AGN perhaps.
That's right. So, well, Yes, one difficulty is that if the gas is removed, if the gas is blown away, if the clouds are destroyed, we're not going to see Maryland emission.
But the shock keeps going.
Yes,
Maybe
well-
AGN is all for 100 million years.
That's right, but the shock keeps going, but it becomes unobservable for us if there are no clouds illuminated by the shock.
Sure, but that's not related to whether the AGN is on or not.
That's right.
Yeah, but her
That's
mission
right, I'm
is
just-
powered by the AGN.
Is that
It's
true?
the photo, oh, that's true, yeah.
It's
you- it's the
photoionized
photo
emission.
ion.
Yeah,
That's
yeah,
true,
yeah,
yeah,
that's
sorry.
right, to a large extent.
But you can also have small scale variability, even 10 to 7 years, that's, large scale. AGN also vary on much shorter time scales.
We do
Yeah.
see dramatic variability of up to 3-4 orders of magnitude in 10 to the 4 years. I mean, we see these flickering AGN, where we still see the light echo, the center is dead, we still see the illumination.
That's in the X-ray, right? I mean, that sounds very, very
No,
small.
that's not what I'm talking about. I'm talking about
There's no evidence that the UV emission from an AGN varies on short times. Timescale shorter than 10 to 4 years.
I'm committed to make it back to Rachel and take a detour through Knud, but that's the last thing to do.
Please qualify what we mean by AGN, because, I think the discussion over the past 10 minutes ranged over 4 orders of magnitude in masses and things, so please say if you mean quasar, AGN, low luminosity, etc., because, we have a massive difference.
Okay, Rachel.
Well, so this is now sort of long ago, but on the question of whether you need to suppress star formation in disks, I think it's all about accretion, right? I mean, I think in everybody's models, the galaxies that are too massive today, that we are bothered by, are early types today, but they're stars all formed in disks at high redshift, right? So, but I think the amount of gas that we know is in those disks at high redshift, if you turned all of that into stars, there's no problem, right? So you really just need to stop the accretion. And I used to think that that was probably done by something like radio mode, but now some of the recent simulations have shown that if you have momentum-driven winds from bright mode, that can actually blow a lot of gas out of the center, or even modify the hot gas profile and also suppress accretion onto a disk.
This is just, I would echo exactly what Rachel just said, except one subtlety I had, which she and I have talked about a lot, that I think there is a second order question. I agree that the most important question is stopping cooling, and if you don't do that, you're never going to quench. There's a second question which isn't clear still, I think, from the observations, which is, do you need to quench fast? Is it enough, however it happens, to just cease cooling from the halo and then let my disk just bubble along in gas exhaust? Or do constraints from the color, just getting the color boundality right require I do something violent that either produces winds or, funnels the gas into the center to exhaust it quickly? And I feel like I still don't know the answer to that question.
the answer is both happens.
We don't know.
Can I just, I mean, this is sort of
You assume.
what I was trying to address in my talk yesterday, which I know you
Oh,
missed,
sorry.
but I think that from what we know about galaxy structure and morphology and how that transforms censorship too, and the size, that you need to get rid of the gas before you merge. That's what I was arguing, right? That otherwise you don't get the size evolution right. So I think that does sort of answer that question. There is a small population, maybe 10% of disks that can just be, just fade away, but it's a small part of that population.
All right, last word goes to Tim.
Okay, so I think you can also get some of this information from the abundances, right? Because your alpha abundances in early type galaxies suggest you need to have ceased star formation before you can reincorporate those metals from the type 1a supernova. And that if you just let this fade, they're going to have time, the Kennigan-Schmidt law, fading time is 2 giga-years essentially, or 1 to 2 giga-years. So you're going to reincorporate some of those metals from those supernova. So it seems from that there needs to be some sort of violent mechanism, whether that's AGN, it's an open question. But.
All right, very good. Then let's thank all the speakers of this morning again.